Okay, so let's do a little geometry then. I just want to start with some basic stuff. And so I want to start to talk about angles a little bit. This angle has a name. It's called a straight angle. And it's measured how much? What measure do we put for this angle? Well, usually an angle looks like this, right? But imagine that that we just sort of move these things around. So here's an angle. These half lines are called rays, like ray of sunshine, and it's possible to have them in this position. That's called a straight angle. What is the measurement? How many degrees is that? Yes, it's 180 degrees. And that was a random choice. I don't know. I think the Babylonians they were kind of obsessed with 60. I think the 60 minutes, 60 seconds, that's because of the Babylonians. I find 180 a nice number because it's divisible by 3, so you don't get those nasty decimals. It's divisible by all kinds of things. 2, 3, 4, 5, 6. I think 7 is the first number where it doesn't work. But you know, there are other measurements. If you get this calculator, you see this DRG there? That's for degree, radian, gradient. Gradient, the British, their straight angle is 100 gradient. And if you take half of that, that's what we call perpendicular or right angle. That's not 90 degrees, but 100 gradient. Doesn't matter. But it was basically some people agreed, and they didn't even ask us before they made this agreement. And now we have to live with their decisions. This here is when you start with a line and you rotate it all away. This is gonna be 360 degrees. I guess this is called a full angle. I don't care about the label too much. And then there are names that are not that important. I will never please you on names, but I hope that you will understand when they pop out of my mouth. This angle is less than 90. Oh, this is also called a right angle. And that's called an acute angle, like a disease that's acute. It doesn't matter. And then an angle that's bigger than 90. Does anyone know how it's called? An angle that's, you know, it reminds me of the word obese. I'm on a diet right now. It's obtuse.
Obtuse,
So,
yeah.
which is another word. It's not, but it just reminds me greater than 90 degrees. It's called obtuse angle. It doesn't really matter. I will actually not often use these labels. Those are important words. These little tick marks, we state that these two sides are equally long. This is called, 2 or more sides are equal, then it's called an isosceles triangle. And if all 3 sides are equal, that's a special case of an isosceles triangle that has 3 names. How do we call a triangle where all 3 sides are the same? Well, I'm going to call it regular. But it can also be called equiangular, which states that all the 3 angles are the same. But equiangular is hard to spell, hard to pronounce. That's why I prefer regular. Or equilateral, which states, I think, literally that the 3 sides are the same. I will just use regular for laziness. It's easier on the spelling and less characters and all that stuff. So what I wanted to show you is when are 2 angles equal? And so there are going to be many cases, but the 2 fundamental cases is when 2 lines hit each other like so, then there are 4 angles formed here, but really just 2, because these 2 angles have equal measure. That's just a very fundamental fact. And there is an expression, these angles are called vertical angles. Another case is when it's a little bit more complicated when you have a pair of parallel lines hit by a third line. So we have, let's call it L and L prime. This is one way for us to say this L and L would be the same object. L and L prime means they somehow belong together. This is how we just sneak it into the notation that they're parallel. But I rather write it down. L and L prime are parallel. And they are hit by a third line. Let's say E. And then these two angles that are formed here have equal measure. And then because of this previous rule, this is joining the part, and this is, so there are really 4 equal angles here that I could color red. And if you have to say, oh, why is that? You could say, oh, because they're vertical angles. What we say here is kind of this third line hitting the pair of parallel lines has a sort of a romantic name. It's called a transversal, like the lonesome traveler. So E is a transversal for the pair of parallel lines L and L prime. And I forgot to mention that these other 2 angles are also equal to each other. And furthermore, what happens if you add 1 green and 1 red angle here? What happens if you add 1 red and 1 green angle? You see these 2 angles. This is what it looks like visually when they add up to 180. You see that? You draw the red angle, then the green angle, and they together form the straight angle. So you have, there is a word for that, but it doesn't matter. They add up to 180. Yeah, there is one more that I would like to mention is when you have parallel lines. It's sort of an angle coped. See, if this is A and this is A prime, and this is B and this is B prime, if these pairs of lines are both parallel to each other, then this angle is basically we just copy the angle. I think that's an important case too. If A and A prime are parallel, and B prime are parallel. So what I want to show you right now, we were getting ready for the following. I want to prove it to you that the 3 angles in any triangle, they add up to 180 degrees, no matter what triangle you're dealing with. But before that, I actually want to get over something just a little bit painful. Is I want to introduce Greek letters we use Greek letters for angles. Now lately this is disappearing, but I think you can handle that. So we will often denote. That means when you are writing your exam and I'm looking at your work and you're not using a Greek letter, you're not going to lose a point, but you will be able to understand, because I will always use Greek letters for angles. They're kind of fun anyway. So there is alpha, which is the lowercase a. When there's this expression, the alpha and the omega, that means the beginning and the end, because omega is the last one. This is their version of A. And then there is, for B, there is beta, and beta is lots of fun to write. It's a little bit like the number 13, but some sort of a genetic, they grew together. The 1 and the 3 grew together. It's fun to write. That's beta. And that's what we will use for the angle that we will associate with letter B. And then for some weird reason, the letter C in Greek, which is xi, it wasn't, people didn't like it. They jumped to the letter G, which is gamma for the Greek. And gamma is kind of fun. It looks like the number 8 after some sort of an accident. This is the letter G, but that's a well-kept secret. So what we like to do is we like to associate. So in a geometry problem, it doesn't matter how things are situated. So if we use, for points, we usually gonna use capital letters. And there is this thing called standard labeling that says that, okay, if you're using A, B, and C for points, then alpha, beta, and gamma cannot go anywhere. Alpha has to go where A sits. That way we don't have to take half a page explaining a geometry problem. So alpha, these points are called the vertices. I will never use it. Those are the points A, B, and C, and the angles are alpha, beta, and gamma. And standard labeling means that once you throw out A, that's where alpha has to go. And beta has to be with point B, and then gamma has to go with point C. That's fairly straightforward. Now, the sides are a little trickier because a triangle has three things: 3 sides, 3 points, 3 angles. So the sides, we usually use whether a line is just a finite line segment or an infinite line or a ray. We use lowercase letters for that. So we're going to use side A, side B, side C. But now the question is, standard labeling means there is just one place where side A can go, but where does it go? If you look at point A, there are 2 sides coming out from point A. So which one should we call side A? Right, here is point A and the 2 sides forming angle alpha. Which of the 2 should we label A? The answer is none of them. Let's label side A, the one that doesn't come out of point A. That's what we're going to refer to as the opposite. So lowercase a goes here. And then lowercase b, you see there are 2 sides coming out of point B. The side B is the only one that doesn't come out of that point. And, you know, this looks like strange at first, but there is something deeply, there is a connection between this angle and this side, because check this out. Imagine that we're playing with a triangle where the triangle is basically, this is 1 point, this is 1 point, and this is 1 point. So mentally, you just have to connect these 2 ends. You see what I'm saying? And imagine that we fix 2 sides, these 2 sides, so these pencils don't get any shorter or longer. All we're doing is we're playing with this angle. Now, if this is the triangle. Now, what's the only side that's invisible? What happens if I close down the angle? Will this side grow or shrink? I'm closing this angle down. What happens? One more time.
See? It shrinks.
Yes, they are very organically grow and shrink together. So in fact, the standard labeling is really, really smart. In fact, the following is true. The longest side is always opposite the greatest angle. So they grow together, and even in comparison, it's always opposite the greatest angle, and vice versa. And vice versa, I mean, the greatest angle is always opposite the longest side. There's a perfect correspondence, and the shortest side is opposite the smallest angle, and the smallest angle is opposite the shortest side. So we can always, if you understand the order between the 3 sides, you understand the order between the 3 angles. Or if you understand the order between the 3 angles, also the sides. So this standard labeling is actually more clever than it appears to at first sight. The shortest side is always opposite the smallest angle. And then the middle side, middle angle, that kind of, it follows from this. And there are some very important consequences. What happens if a triangle is isosceles? Isosceles, remember, means that two sides are equal. Well, then, if two sides are equal, then the sides opposite those equal sides are also equal, and vice versa, which is a very, very useful little fact. So if two sides are equal, then the angles opposite them are also equal. And vice versa. If two angles are equal, then we can conclude that the sides opposite are equal. And angles opposite them are also equal. And vice versa. I'm just going to do this, which means this implication goes both ways. I don't want to waste your time with just writing. So if we have something like this, then we can conclude now this side is opposite this angle, and this side is opposite that angle. And so these two angles are also the same. I think it's more often than we notice that the two angles are the same, and we conclude that then the sides are the same. That's very, very common. All right. So now I just wanted to get standard labeling out of the way. Now we're going to go back to prove if alpha, beta, and gamma are interior angles in a triangle, then alpha plus beta plus gamma equals 180 degrees. The word interior is kind of goofy. You don't have to ever worry about it. This would be an interior angle, and then this would be an exterior angle. I shouldn't even have included it. All right, so we're going to prove this fact. Okay, so let's say this is A and B and C, which means that angle alpha is here, angle beta is there, and angle gamma is there. And where is side A? Side A is where? Where is it?
Opposite between C and B.
Very good. Sometimes people say A or side BC, but honestly, I cannot read stuff like that. It's too much work. But side BC is the same as side A, but it's just so much more. Very good. So now we're going to prove that these three angles add up to 180. I'm just looking for space. I think I kind of messed up, but okay. We're going to do it here. Labels are always in the wrong spot. Okay. So the first thing we're going to do, I'll put the picture back. So first we're going to draw a line through point B that is parallel to lowercase b, the side. So what that means is that I'm going to make this line a little longer. This is it. So here is, this is point B. I just don't know where to put the label. It's going to be on the way in. It's going to be at the wrong spot. I don't know how that's done, but I'll put it at the end. So this line is now parallel, and then we're going to extend these two little lines here too. Okay. All right. So and that's it. We basically are done. We just don't know that. What is this red angle equals to alpha or beta or gamma, and if so, why?
Because it's a vertical angle?
Yes, they're vertical angles. Very good. Okay. Just to go back to it, I love this about Zoom that, you know, once the chalkboard is erased, you cannot go back, but here they are when two lines are hitting each other like so, these two angles and also those two angles are vertical angles and they have equal measures. So we have that there. So beta equals to the red angle because they're vertical. And as it's gonna turn out, this angle here is gonna turn out to be equal to which angle? Alpha. Why is this alpha? I'm gonna call this line B prime here. Why is this blue angle alpha? It's that other more complicated case when you have a pair of parallel lines hit by a third line, then these corresponding angles formed are the same. You need to squint a little step back a little bit and see, here is a pair of parallel lines, and now this is a lone traveler, a transversal, hitting that pair, and therefore these two angles have equal measure. You kind of have to ignore the rest of the picture, and the picture should be realistic. Realistic pictures are so important. Always try to be as close to the reality as possible, because you will see things. See, these two, there is a pair of lines hit by a third line. So the blue angle equals to alpha, or alpha equals to the blue angle. And if someone says why, and it's hard to explain, we're just going to say that the third line, namely C, is a transversal to the parallel pair B and B prime. And then it's going to be a very similar argument why gamma is going to be this one. You see it?
Yes.
Good. I lost it for a second. So we have a pair of parallel lines, and now the transversal, the third line hitting them is not C but A. And then these are formed there. So another transversal case means that gamma is the green angle. And now look at these three. When we pile them up one after the other together, they form a straight angle. And that's the proof that these three add up to 180, then, well, better these three add up to 180 as well. So gamma equals to the green angle. The parallel pair is just B and B prime, and thus A is the transversal. And now from the picture, oh, here, maybe I can do this trick. Nope, it's not gonna fit. So from the picture, the red angle plus the blue angle plus the green angle equals to 180. But the red angle is the same as beta, and the blue angle was same as alpha, and the green angle was gamma. Was it? What it was. So there it is. See, we did a lot here. For example, let me ask you this. What are the angles? What are the measures of the angles in a regular triangle? A regular triangle is characterized by all three sides are the same, right?
Is it 60?
That is right. You have three angles that add up to 180, but they have to be equal. So that's sort of x plus x plus x is 180. That's 3x is 180. It has to be 1/3 of, yeah, it's 60, 60, 60. I know we haven't done equations yet, but it's x plus x equals 180, 3x equals 180. So x equals 60. But you don't need to do that. We don't need formal equations just to sort of figure out that three equal numbers add up to 180. They have to be 60 each. All right. Let me ask you one more thing. So one angle in an isosceles triangle is 40 degrees. What are the other angles? What is the measure of the other angles? What are the measures? I think you got it.
70?
70 is good. That would look like, wait, 70, 70, 40. That would look something like this. I'm trying to make it realistic. It's too big for, yes. But that's not the only option. There are two possibilities. Because I didn't tell you whether 40 is the standalone guy. So if 40 is the standalone guy, that's a little too skinny now. If this is 40, then how did you get 70? Tell us. You got it right. How did you get 70?
140 divided by 2.
How did you get 140?
I took 40 away from 180.
Exactly. The three angles add up to 180. Well, we have accounted for 40, so these two have to add up to 140. They have to be equal, so that's 70 and 70. But what if you have 40 repeating? What if you have 40 and 40? Oh, that's a terrible picture. What's the third angle? If you have an angle 40 in a triangle and another angle that's 40. Let's think of 40. That's more like realistic. I actually have a protractor, it's called. How do you call this creature? The one you use to measure the angles. Protractor. All right, I forgot my glasses. Okay, I see. There's 40 there. Oh, but I would need 40 from backwards here. So it's 180, 140. That's 40 degrees. I'm still waiting. So the third angle, I finally managed the 40 degrees angle. It took me a while, but I think I managed it.
I'm going to be 100.
Exactly. So you will see this or sort of something like this in the homework. 40, 40, that's 80. We need 100 more. And then in this case, what you have to enter, basically when often there is more than one solution, the question was a little clumsy, but intentionally so. So the answer is going to be, well, the other angles are either 70 or 100, depending on what angle causes, what angle is repeated, the 40 or that other angle. If the 40 repeats, the other angle, the third angle is 100. If the 40 is the standalone, then the other angle that repeats is 70. Kind of a cute problem. So I kind of want to show you how mathematicians are basically, they're very lazy creatures. I'm going to keep repeating that. And we like to use what we worked for. So what about the sum of angles in a 5-sided polygon or a 10-sided polygon? Poly in Greek means many. So polygon is, it's like a triangle, but it has more stuff. We don't state 4 or 5. This is a 5-sided polygon, and in Greek, 5 is penta. That would be the pentagon. What about the 10-sided polygon? Actually, in a way, I think a 10-sided polygon is easier for me to explain to you, because a 5-sided, it might force you to, well, all right, let me just show you. So we're gonna do the 10-sided polygon first. 1, 2, 3, 4, 5, 6. Okay, we're dealing with a 7-sided. Luckily, the number of vertices and the number of sides is the same. We could have gotten much more unlucky. There's a lot of times there is a little glitch. Okay, it's 7. Okay, this looks regular, but it doesn't have to be regular. All right, so we're gonna first throw in an extra point. And triangulate the poor thing. Basically, we're going to exploit the following fact. Well, we just worked really, really hard to find the sum of the inner angles in a triangle. Well, let's use it then. So I'm going to throw in a point in, it doesn't have to be centered. It doesn't have to be regular. And now we're going to create triangles. Why? Because we know that the angles in any triangle add up to 180. So these blue angles, we don't know them separately, but their sum is for sure. What is the sum of these three blue angles?
180.
180 degrees. And then the sum of these red angles is also 180 degrees. I think I'm going to run out of colors, but you kind of get the idea, right? Once I'm done with, okay, we can use a black one, I guess. Okay, I ran out of colors, but you got the idea. If we mark everybody, all these angles that are marked together, what is the measure of the sum of all these marked angles? Just gonna use a, I have yellow somewhere, don't I? So now that every angle is marked, what is the total sum? Oh, there's an answer in the chat box. I don't even know, but it's 7 times 180, right? 1260 is correct. We can correct, my favorite combination. But this is not exactly what we wanted. What we wanted, this angle is part of the deal because the red and the blue, that's one angle we want to add. This is something we want, but you see, we artificially threw in a point. So these angles here that were created, these are extra. We don't want that. That's the overcount. If we could just know what these guys add up to, we could subtract that. So the overcount is this here. What is the sum of these angles in the center? 360. That's the overcount. So 7 times 180 is too much, but luckily we know exactly how much too much. It's 360 too much. Right? And so what was that? 1260 minus 360. It's going to be 900, right? Minus 360, and that's 900 degrees. So I didn't even know that the 7-sided polygon, all of them, it doesn't have to be regular. It has 7 sides. Then the sum of the angles is 900 degrees. What about the 10-sided? Try not to remember formulas, but just the methods. Try to remember a story. So for a 10-sided polygon, maybe we don't have to draw it, but we can imagine that we throw in a point in the middle and we triangulate that thing, right? We throw in a point in the middle. There is no middle. If the thing is not regular, there is no center per se. Then we triangulate it into as many triangles, as many sides are there, and that's 10. And then each of these little triangles, the 3 angles add up to 180. So we have 10 times 180. And the overcount is always this full angle, 360. So that's a pretty good formula we just developed. 360. I'm going to call it, so the chat box says, oh, it's 360, not 420, because the measure of the full angle is 360. Exactly. That's the circle, you call it. Yep. That's why. So it's 1080 minus 360. 1080. Wait. 1800. Jesus, I get worse every semester. So to multiply a number, an integer by 10, we just need to toss in another 0, but 1800 minus, oops, 1440 degrees. That's a lot of degrees in a 10-sided polygon. That's the sum of, so the sum of all angles in a 10-sided polygon is 1440 degrees. Okay. Okay, so here is what happens. I'm gonna color sides, and the sides with the same color. No, the red sides are all equal to each other. So these are all equally long line segments. And the question is, this here is 10 degrees. What is this angle? This is what I call chasing angles, and chasing angles is fun. Any ideas? Hold on. Let me give these points names so you can talk about it without having to show the EF. Okay, now we can talk about it a little easier. What can we first find? Is there anything that we can find here? Who is 10 degrees? Right? This here is an isosceles triangle, right? AB and BF are equally long. That means that the angles opposite those two are also equally equal in measure. And the picture is kind of obvious. This is a huge obtuse angle, right? This is not going to be 10 degrees. This is on the other hand is 10 degrees because these two sides are equal to each other, right? Good. Now what can we find next? Now check this out. The notation is terrible, but if we want to talk about this angle, we can say AFB. AFB is 10 degrees, right? You just sort of walk it. You name the points that you touch as you walk that angle. Same as BFA, because ABF is isosceles. Now, what can we find next? B, this angle, because if you know two angles in a triangle, you know the third angle. So let's find, I'm not sure, you know, every time I said there is no other way, I had to eat my words, so I never say that anymore. But clearly we can find angle ABF just because we know two angles in our triangle, right? What is this angle?
160.
Yep. ABF is 180 minus 10 plus 10. Right? Okay, what can we find next? Actually, that would be an exterior angle. This is the stuff that we can find next. Maybe that's the trickiest part in this problem. How much is this angle there? And why?
20 degrees.
20 degrees, exactly, because these two together, they form a straight angle. That's 180. So this is 20 degrees. And it's kind of funny because if you look at the world from the point of view of this big fat angle 160, then the other two angles when added to it has to be 180, and so is this. So it's a kind of a rule that this exterior angle is always the sum of the other two angles, because they share the property that when added to 160, it better give us 180. So that's generally true, that the sum of these two is the same as that. So our step 3 would be that angle FBC is 180 minus 160, which is 20. What can we find next? I'll give you a hint.
BCF.
BCF, because again, this triangle too is isosceles, and the measure is the same. So that's 20. Now what? This is a notation for triangle. This for angle BCF is isosceles.
Angle BFC.
Angle BFC is how much?
I want to say it's 140, but the line is throwing me off.
You're right. You know, I like, so basically that angle looks much smaller than 140. Is that what you're trying to say?
Yes, because it's
go ahead.
Next.
That's because my picture was not realistic. This angle is way too big for 10 degrees. 10 degrees is, and I like that kind of measuring your results against common sense, and that's just a beautiful instinct that you should keep, even if it gives you red flags sometimes without a good reason. And then that will help you to draw, next time around you draw a better picture, because a good picture in geometry is more than half success. Because to draw a good picture, about my other program, to draw a good picture, it's almost 20 degrees. And that's why if this was 20, 20, 40, this would be 140, this would be 40, this 40 plus 40 is 80. This is good for 100 degrees. So what happens is the picture wasn't realistic, but beautiful catch. But it is 140. And then it's a good little fun thing to draw it correctly. This is my other protractor, but it's a little red. Yeah, this is 140. But it looks more like 100 than 140. So this is where the picture is not realistic enough. Now what can we, very good point. What can we find now? Oh, it's this guy that we can find now. How much is that guy? And again, the picture is bad. So keep that in mind.
Is it 40 degrees?
No, because you see, this is standing there. So these three together form a straight angle. So it should be 30. And this is way too big for 30. And I'm getting worried that maybe this is going to turn out to be a negative angle, bigger than 180. I hope not, but it's getting really bad. Now, what can we find next?
Angle FEC.
It's also 30, right? Bad picture. This would have been a much better problem if this is a 20. And then this angle is how much?
130.
130, 120.
Oh.
Yeah, this is just a disaster. 120 plus 20 is 140, which makes this angle
40.
Although it looks more like 80. And that means that what we were looking for is also 40. Just for kicks and giggles, if we double this, I think if we double this into 20, which would be a better picture. 20, 20, 140, 40, 40, 40, 100, 20 plus 100, this is 60, perfect, 60, 60, 60. This was 40, 40 plus 60, then it is actually 80. The picture is perfect if I just wrote 20 degrees there, which is what it is. But it also shows you the value of realistic pictures. But this one, the answer is 40 degrees. With my apologies.